Hi, I am Kim Yuji, a joint master and PhD student. Today I want to introduce Tae-Hyun permutation-equivalent visual geometry lab. I selected this paper because my research collaborators have repeatedly said that the results are really amazing for this paper. So in my opinion, reconstruction quality is one of the most important aspects in the 3D reconstruction field. So today I want to introduce this paper. Reconstruction is crucial to the 3D geometry and has been a key research problem for a long time.
소리가 마이크
혹시 이 정도로 하면
네.
가까이에서 네. Reconstruction task 너무 크진 않아.
아니요 지금
네. So 3D reconstruction task aim to recover point cloud and camera points from several unconstrained images. And the recent trend is the visual geometry reconstruction with the feedforward members. So I would suggest that this approach is the current paradigm in the 3D reconstruction. The input of this task is the set of uncalibrated images, and it is meaning that the corresponding camera points are unknown. Based on this, we want to reconstruct the 3D representation along with camera points. So today I want to focus on the point map representation. And I want to introduce the brief history of the visual geometry reconstruction. I think many students or researchers are familiar with this visual work, so I want to briefly introduce this. The first one is the duster, and it is the initial approach to reconstruct 3D point map from the uncalibrated images set in a feedforward manner. And monster is the following work to produce a time-varying dynamic point flow. And both of these papers were covered with in the Junsang seminar, so if you are interested in, please check this. And the subsequent work addresses continuous and the streaming input. And since it also already been discussed by our last seminar, so I will skip the details here. And the vggt is a new framework for visual geometry reconstruction. It is also a feedforward neural network which can directly infer or 3D key attributes such as camera, pose, depth maps, point maps, and some correspondence. And this is the stage of the artwork in this field, previous to this PySwitch. And vggt is the baseline of this seminar paper, so I would like to introduce it in more details. Test reconstruction method also rely on some test optimization. For instance, a map incrementally register images while repeatedly finding 2D correspondence and performing other adjustment. And a recent deep learning framework is a duster, and it predicts a pairwise point map and uses a global alignment for their vision. So they their estimation in order to distribute, and so this is just some global optimization process. So all of these previous methods were the time-consuming optimization process. So optimization is very time-consuming process. So it takes several seconds or minutes to get some result. also this optimization framework is hard to integrate with some deep learning framework with some plug and play method. And optimization is also has some complexity, means that it relies on some complicated engineering techniques. To mediate these issues, vggt proposed their result, and given some uncalibrated images, they use some neural network. And with only this neural network, they cover their diverse 3D properties with only one reinforcement. This is the detail of their network. And given multiple uncalibrated images, first they predict the dino feature and multiply these to fit the transformer models. And this is the uncalibrated images, so they add some additional compute token to aware their positions. Yeah, and as I explained before, they have some many 3D tributes, so they train all of these compounds in the end-to-end training manner. So the architecture is very simple. So VGT is don't need to time constant optimizations, and they can get some comprehensive outputs, and their result is also simple and efficient. But this previous work also have some critical limitations, and PyCD point out these limitations. The most important thing is that they have higher reliance on selecting a single X level. So previous total method, VGT, is highly sensitive to the initial field selections. So this is some result for the sensitivity for the resolution. So the green line is the VGT result, and the x-axis is the varying frame index. So as you can see, VGT produce unstable result depending which reference frame is selected. So PyQ suggests some lower scalar and only permutation equivalence method. So it means that with this varying frame index, they don't have any unstability for their cavity, and they also have some scalar result compared to this previous work. And for this permutational equivalent property, they designed two attributes. First one is for the camera pose, and second one is for the point length. And I will explain the details in the next part. So this is the overall pipeline of the PyQ. The upper is just show the previous methods such as VGT. And the key component is that they use some reference indicating modules, and they have some methods such as concatenating some additional positional tokens such as VGT, or just adding the another positional embedding. But the difference from this previous work is that just they remove this reference indicating module. And the overall architecture is similar to the prior method, but the only difference and key difference is that they don't have any reference indicating module. So by eliminating this dependency, PyQ achieved robust and improved accuracy. So I think the idea is very simple, but the result is really nice. First I want to introduce for the permutation-equivalent property. And I think that most of you already familiar with this property, but it is a core idea of this pipeline, so I want to explain. And S is denotes some input image sequence, and pi is the network. And this is just some equation for the network input, and the output is some set of the camera pose, throughput map, and the confidence map. And the input and output are the same as in the prior work. So the permutation equivalent property means that the network needs to satisfy these properties. So in other words, the output of this permutated input sequence should be the same as applying the same permutation to this network output. Yeah. So in this paper, they want to implement this property, and they propose these two methods. So the first proposed method is the scale invariant local geometry, and it is for the point map prediction. So they remove their positional aware part, so they need to improve this. So yes, so for the point map prediction, there is a challenge to achieve some permutational equivalent properties. If we assume that we have some permutational equivalence, we need to define prediction process. Prediction result is in their own camera coordinate. In other words, it means that we do some molecular estimation for the each peak. So the well-known challenge in the molecular estimation is that the scale ambiguity. So the main challenge in this work is to how they handle the scale ambiguity in the point map and the camera pose. So the solution for this point map prediction is that they just assume some consistent but unknown scale vector. They just pick some value, and they want to serve these scale vector with some zero optimal values. So they minimize the depth-weighted error loss between the point map, predicted point map with scale value and the GT point map. So they want to get these optimal scale vectors. And they use depth-weighted error distance because to get the higher weight to the near one and the low weight to the far one. So the previous one is for the point map prediction, and the next one is for the camera pose prediction. So for the camera pose prediction, they also have some scale ambiguity also. So our camera pose are only defined up to an arbitrary similarity transformation. And I think most of you also heard about the similarity transformation, and it is just a linear transformation with scale in here. So in here, they also have some scale ambiguity in the camera pose. So to serve this, they summarize only between the related camera poles. So they don't consider any global camera frame. So I want to get some detail for this solution. So as I mentioned before, they supervise their network only with some disrelated camera poles, and this is the notation of the camera poles from the view J to the I. And time pose has two parts. First one is the rotation matrix, and second one is the translation. So for the first rotation part, rotation is the invariant to this global transformation, so we do not need to consider any scale ambiguity. So for the rotation laws, they just use some geodesic distance between the relative rotation and the duty rotation. And the geodesic distance finds some surface distance between the 2 points on the curved surface or manifold. Because rotation groups has curved manifold, so we have to use geodesic distance, and we cannot use the Euclidean distance in here. And this is the loss equation. I think this Rodriguez formula is the most famous angle equation. So just use this and convert like this form, and convert like cosine, we can get this relative angle. So based on this, we minimize the difference between the relative rotation. And the second part is the translation. And relative translation has a scale ambiguity, so we need to handle it. And for the translation laws, they simply use the Hugo laws for its logoses to the outliers. So they measure the loss between the ground truth relative translation and the scale predictive translation. So this is the R of these Carapos estimation part, and they just weighted sum between these two parts for the or easy use. So this is the final model training objective, and this L point is for the point map, and this L cam is the Carapos matrix. And they also add some additional two part. First one is the normal loss for the locally smooth surface, and this is for the computational loss. They use the binary cosmology for this. So that is the end of the method section, and next I will present the experiment result. So before moving on, are there any questions for the method?
That's scale ambiguity.
Yeah.
So you mentioned that you have to solve for single scale vector so that it can minimize the elements. That's just, but I guess this solving should be differentiable. So, is this operation differentiable so that you can like train the full model session? Is it like test?
Can you say the last word? Okay.
Yeah, so I mean, what I understood is that we have to solve for, we have to align the like per view predicted point maps during the training session of this model. But I guess this solving pipeline should be like in answer. So is it like or is it a detached solving stage?
So as I understand, you ask that the update parameter is only for this scale of the R of this easily. 제가 제대로 이해하고 한번 다시 주세요.
그 모델 학습을 위해서 이걸 맞춰줘야 되는 모델이 정말 스케일 벡터를 잘 익숙하는 편이죠. 제가 이야기한 거 그러면 모델이 그대로 필요한 포인트 벡터를 얼라인을 맞춰한 스케일 벡터를 솔빙을 할 때 그게 모델 트레이닝 룩 안에서 디퍼런셜가 일어나는 거.
한국말로 먼저 하고 보겠습니다. 제가 이해하기로는 일단은 앞에 여기 첫 번째 써 있는 것처럼 일단 그 특정한 S 값을 그냥 픽스를 하고 이제 파이프라인을 옵티메이션 하는 부분. 이 S 값을 풀기 위해서는 이 이케이션에다 특정한 솔버를 쓰는 걸로 보면 돼요.
그래서 그 솔버가 디퍼런셜을 한다고. 이게 디퍼런셜에서 모델 학습, 그러니까 그 솔버로 푼 어떤 이 모델 학습을 줄 수 있게 디퍼런셜.
So what you say is the scale factor S star is pre-calculated before the training and the fixed and applied to during the training. But I don't think that that's the really the case. I'm sure because in order to estimate the scale ability, we need to first know exact depths and the all the components beforehand. So it's kind of a chicken and egg problem. So there is no way to we can get the depth scale ability before estimating any depth. So yeah, I think that you need to follow up the exact procedure, and also I have the same question with the one because without estimating the accurate scale, we couldn't estimate the accurate point map. But without estimating the accurate point map, we can also get the scale factor because those are kind of entangled optimization variable. So maybe I thought maybe there must be some kind of test time refinement procedure to define the scale factor here. But you say that it's not. I'm a little bit confusing. How can you get the scale up? How can you solve the scale up?
I understand that this is correct, but I think that we don't need to know some scale for this consumption. So I think that we just prefix this value and just share across the phrase. But it is okay to any scale because we don't need to define result later. So just fix this and I understand to serve this after the outline. After the only point is one single table scale.
In this objective function L point, what is the optimizing value? S star and the X cap. And Xij is the ground truth information from ground truth set. Then you need to know some initial point of the X hat as well. Where do you get? Then you need to know the initial guess of the scale factor. Then maybe train it. But the problem is, since this objective function assumes the IID edition of the geometric variable X hat, so there are lots of the trivial solutions you can satisfy. So there must be some additional regulator to preserve all the structure according to the ground truth set possible, while satisfying the single from scale. So scalability problem is a non-trivial problem. So I'm not sure whether we can naively solve the ultimate scale factor. Anyway, I think that this procedure may you need to just very specifically and detailed understand of this procedure. The small details are very here, so that maybe the better follow up better.
Yeah, I understand. I'll go later here.
So is there any stage for the curriculum?
Oh, as I know, there's no curriculum.
So they train. So so the object function is defined for training the neural network for object. So it's not the test count engagement.
Yeah, there's no.
Then there must be some assumption.
Yeah, I'll check it here later. Thank you for the
So has the same question. So I think I also read the paper for here as the optimized single scale vector for the whole images and the training procedure is just a one step. I mean, there's learning. So I think the scale vector will have to consider all the different data set, and I think there should be some kind of error because single vector has the cannot contain the values data set and but on the other hand, I just wonder maybe use the rotation of translation, rotation offline variables. Then yeah, and there's the ground truth that means they use the ground truth camera pulse for that, or there's other way to calculate the camera pulse translation transformation.
As I understand, the first question is that there are many variables in the white data, so how we cover all these single scale vector can cover the whole data set. And the second one is, I think I can see
You can start from the first one and then
okay.
한국은 네, 다양한 데이터셋에 대해서 하나의 싱글 밸류 옵티마이즈를 한다는 아이디어가 있는데 말씀하신 것처럼 가상이 없으면 다양한 데이터셋을 싱글 밸류로 주는 게 무조건 에러가 있거든요. 그럼 저자들은 에러를 감안하고도 옵티마이즈를 한 것인지 스케일이 있습니다. 어떤 이게 방문 운동가 증명이 되는지.
As I understand, they train with very various data to cover the most of the scenarios such as the indoor, outdoor, or the static dynamic and all that. So I think they train with very large scale data set that can cover some. They immerse their information and system.
More specific of the answer is the scale factor is defined within a single scenario. Yeah. So per scenario, it has a different the scale factor. So across the data set, within a single data set, there will be many varies. One take, and second take. So each take of the scene have a completely different scale factor. So for each episode, we need to get this scale. And I think that I get that. So I think that this single scale factor is obtained from the pre-processing, but under the assumption that I think that this train data is pre-processed. So it's a little bit different from the vggt. I think that they learn the call map or those kind of structure from motion pipeline first to get the all the ground truth translation and rotation and 3-point all of that as ground truth. So then that makes sense.
I don't know
Yeah, so that part is easy, but that's why the race is something.
Yeah, if it's different, I also check I don't know the different
In this world, the trade
in these we're training
Yeah. So here the ground truth 3D point, and also there I can see the ground truth translation, ground truth rotation in every objective function, which means you already know the ground truth rotations, the translation, and also the what was it? The 3D points, which are obtained in a past.
Yes, I understand they already have all of these data in countries, but maybe they don't know the comment, but the original data has all of this information. They didn't create some normal process.
So without that structural promotion, how to do that?
Mm,
And that's also that raises another question. I feel like the X here is map. That's like a top pixel dense structure for 3D. And then where did you get? Because the structural motion or the whole map hyperlink only provide a very sparse 3D, not top pixel dense.
I understand. For example, when we use the scannet, they already have pattern image and the depth and the camera pose all of the information, so they can input the preview information. So as I understand, they
So
already
why the 3D just scan map?
they include scannet and
Include the
very wide range of the data settings.
So then where did you get the dense depth map? You scan it? Measured from the depth sensor.
Yeah. Yes. You know, like,
So let's move on.
what is the next question?
This question, I think, is the ground truth. I think the ground truth camera point is the given, right? Because I asked the question because very background of this seminar, there are the problem about the uncalibrated images that we don't know the camera pose. So I just wonder they use cameras that I don't.
Oh yeah, they in the ground truth they already have, but they also in the inverse line they don't have any kind of information. Any other questions? Okay, let's move on. And let's start for the experiment section. Pi cube shows the robust and fully permutation equivalent result as I previously shared here. And they also show the state of the art performance between various data set and evaluation matrix. They also show the scalability of their method. So the PI means the operation of the permutation equivalent, and compared to the without PI, with PI setting show more better convergence and more scalability feature compared to the without PI. PI sets. And they also suggest some interesting insight for their offline invariant camera model. So they present that the real-world camera paths are highly structured and not random. For example, people take images with some trajectory, or for example, orbit the object or along the spheres. So if the camera path is structured, the maneuver space of this camera both shows some low the camera path structure needs to use low magnetic structures. So this is the result of this is the evidence of this. This is the evidence of that. So for the position eigenvalues, they show higher eigenvalue for SB2 values. It means that they are in some low maneuver space. And for the location, it is also same because it only has one high eigenvalue compared to the VT. And this is the quality result, and the pie cube produces more cleaner and more accurate and complete reconstruction with fewer artifacts. And I think this is really good result for some indoor-wide analytical sets. So PyCube demonstrates some superior robustness on some challenging indoor-wide cases. For the quantitative results, they also show some very various tests here, and they also show some state-of-the-art improvements across our benchmarks. They also show some the evaluation study here, and also show that the full model show the best performance, which means that our components are essential. And the final is I manually log the result. So yes, as I mentioned in the first, my research collaborators have said that this work has impressive results, so I want to test it, and I tried to reconstruct the 3D structure with the Hamilton method for certain dataset, which I am currently using. And the left one is the 3D case result. I tested with the 120 frames, and it is not dense view because this scene is very wide and a multipolar dataset. So the reconstruction quality is really poor. And I also test the same interference with the PyCube. And the amazing thing is that they only take 85 seconds to recast this object, and I think it really well casts up even with the multipolar side. So
Are the loops are really placed on different floor or is are
no, really, it is really multipolar data, so it is really hard to, yeah. And the 23 is the traverse between multiple doors. So I think it's really hard case, but it works really well. So I want to suggest that if you need to use some different model, or to use this model. So let's summarize. So in conclude, let's summarize. So PyCube suggests the new paradigm of the fit for the visual geometry reconstruction. So the key idea is that they eliminate the reliance on a fixed reference view. It is a really simple idea for the reader to solve. And I discussed with these students that it is also important to add new things, but it is also better to remove what is unnecessary. And it is in my aspect, I want to in my aspect, I specifically want to improve this part because I want to use this in my project, but it is hard because it is the uncapable setting. But for the embodied or the robotics test, we need to work with some exact camera given pose. So, yeah. And it is also valuable to integrate with the 3D test because it is also valuable for the web synthesis task. And it is all of my presentation, and are there any questions for them?